We now want to understand how the results from set level will be applied at the VVMethods project. And for this, we have also another trio prepared for you. We have Roland Galbers from Bosch joining us via Teams. Roland, good morning. Welcome to our session. You are the project lead of VVMethods, and of course, you engage in several publications and patents as well. So we are excited to hear from you. And you are accompanied by two other colleagues here physically on stage, Dr. Christian Neurohr from DLR. You are a researcher for the sub-project lead for criticality analysis in VVMethods. And the colleague joining us as well is Philipp Rosenberger from TU Darmstadt. Welcome. You're a research associate and part of the working group for the sensor model specification and validation. We are excited to hear about VVMethods. The stage is yours.
Thank you very much, Laura, for a kind introduction. So this is now our chance here to explain something, how can we use the simulation for the release. Please click the next slide. Yes, perfect. So we both projects share a common history. From the Pegasus approach, we both have the aim to release highly automated driving, and where we, as VVMethods, provide methods, we need set level to provide simulation. And this is how we work together, and I come next to the main idea how we work together. And after this, of course, Christian Neurohr and Philipp Rosenberg will tell really interesting applications of this. So let's please get the next slide. Here you can see one in the mainframe how these projects work together. In the morning, Mr. Heigl, for example, explained these three levels of simulation-based engineering tasks. And above you can see how our project has developed, or what our project developed, a core idea, how we can argue. And you see a framework which is done or is made to support the argumentation. It got three layers: the capability layer, the engineering, and the real-world layer, and these perspectives support the argumentation. And please click. And now you see the simulation-based engineering task analysis exactly fits to the capability layer, where we analyze what our project actually has to fulfill. Then simulation-based optimization, please click, reflects the design part, and simulation-based tests reflects the testing and verification and validation part. Please click again. And to the first and the last part, Christian and Philipp will give the detailed application. Please get the next slide. So, thank you. In the first part, now you see, now I like to give you in a nutshell, what is the link between these both projects, how they work together. I told about that for us, the argumentation is the main idea to argue that highly automated driving is safe. But such an argumentation has claims and subclaims and arguments. And a lot of this is like a big network of argumentation. And each of these claims and subclaims, these arguments need evidences. And this is where set level comes into turn. Please click. Now set level, yes, thank you. Now set level is the provider of evidences, of important evidences, simulated evidences. And but in the morning, Mr. Heigl explained a lot about how important it is to exactly specify what the simulation has to turn out. And so please click again. And so what is, for example, the objective? What is the environment and what is the system under test? Really clearly defined. And if our arguments now here our arguments now can clearly define these three areas, because if these arguments give the real, let's say, configuration of the simulation task, then the evidences on the other hand side exactly fit the claim. And this is the circle, and this is the nutshell I want to tell to you. So when we argue, the arguments directly define what a simulation-based task has to turn out, and then the evidence suits. And so our argumentation at the end fits, for example, to argue that highly automated driving is safe. This is the nutshell of the link. And now I'd like to have the pleasure to link over to Christian Neurohr to see a direct application in the criticality analysis. Thank you.
Yes, thank you, Roland, for the nice introduction. And yeah, so now in the VNV methods assurance framework that Roland already introduced, we are in the capability layer, and more specifically, the criticality analysis, which I'm going to present, is concerned with structuring the operational domain, and therefore located in the operational concept and contributing to the derivation of the target behavior. Yeah, what is the criticality analysis in VVMethods? So as a definition, we took the criticality of a traffic situation as the combined risk of the involved actors when looking into the future. So the situation is continued. And yeah, in VVMethods, we are also looking at the use case of the urban intersection. So we are considered with the OD of urban cities. And our main goal is to gain knowledge on the open context regarding the emergence of criticality and its conditions, which will eventually lead to a structuring of the operational domain. In this process, there are several artifacts which are central to this criticality analysis. The most central artifact are the criticality phenomena, which are influencing factors within the operational domain that are associated with increased criticality. And we want to understand these influencing factors. So we are looking at the underlying causalities of these criticality phenomena, which we call causal relations, and eventually these will lead to the derivation of target behavior and also to safety principles that can be taught to automated driving systems. And finally, we take these criticality phenomena and causal relations and really feature them in abstract scenarios, which is the contribution of the criticality analysis to the scenario-based verification and validation overall. So let me introduce you to the basic concept of the criticality analysis really quick. So we have these associations with criticality phenomena. They can be identified through knowledge and data. There are various ways to do this. So the critical part really is to get to the bottom of it, in that we want to understand the causal relation that belongs to this phenomenon, which is then plausible causality at least. And we want to prove our understanding in an iterative cycle of data analysis and expert knowledge interacting with each other. On the way of this process, it might be necessary to acquire some data to base our analysis on, and also we have to update the tools that are used by the criticality analysis. And central tools that we use are ontologies for the management of knowledge. We use criticality metrics in order to make this definition of criticality quantifiable. And most importantly for today, we use simulation to carry out experiments that are maybe too dangerous to carry out in reality. And in the end, we have a convergence criterion of this process where we assess whether we explained all the associations that we found in our databases. So this process relies on two very basic assumptions about the nature of reality, if you so will. One is that the set of the criticality phenomena is limited and manageable, which supplies us with a finiteness of artifacts. And the other one is that we are actually to identify the relevant phenomena in our databases. So we assume that they leave traces somehow, which will give us the completeness of artifacts of this process. So the basic concept really is going from associations to causality. So how are we using the simulation-based analysis provided by set-level within the VVMethods criticality analysis? So for this, we have some minimal required functionality on simulation. We need to be able to sample scenarios from large scenario classes, and in the best case, it's also representative. And one example of this in the current terminology is the instantiation of logical scenarios using parameter variation. Another basic functionality is the execution of concrete scenarios in a simulation. And of course, the evaluation of criticality metrics. So common examples include the time to collision or the post-encroachment time. And but this basic functionality is provided by the set-level simulation use case 1, which also is named criticality analysis, so this is not a coincidence. And how are we using this in the VVMethods criticality analysis? Well, the abstraction and refinement of criticality and phenomena and causal relations can be aided by the use of simulation. We have this large application area where we try to engineer new criticality metrics or find target values for existing criticality metrics and compare such metrics between each other. So this is a very important use of simulation. And on an even deeper methodical side, we want to use it for the plausibilization of causal relations, where we really check real-world data versus the model that we implemented, and also in order to evaluate the effectiveness of safety principles, such as when it rains, maybe you have to drive a bit slower, or when there's an occlusion, you can already anticipate something. Such safety principles, they can also be evaluated in a simulation, whether they reduce the criticality that's emerging from a causal relation. So for the rest of the talk, I'm going to dive a bit deeper in this application called plausibilization of causal relations. On the right, you can see a graph that represents a network where in green we have a criticality phenomenon, occlusion, so we are not able to see an object because it's visually blocked by another object. And we want to understand how it affects criticality and especially its effect on the required acceleration. And the orange variables that you can see, they are the adjustment variables which we have to be especially careful of. So you don't need to understand this graph in detail at this point. So let us look what's necessary for this simulation-based analysis task. So in the criticality analysis, we usually start with some abstract scenario that features the phenomenon. Here we can see some very general urban occlusion scenario depicted as a traffic sequence chart. And our analysis task now is to generate data for the relevant random variables in this graph that I just showed. Based on these orange adjustment variables that can be identified via graph algorithms, we want to evaluate in many scenarios whether the phenomenon is present or not. And of course, we want to measure criticality with a suitable metric, such as some TTC or required acceleration, or whatever fits the purpose of making criticality visible for that phenomenon. And as an example, then we go the step from the abstract to the logical scenario. For example, on the bottom left of the slide, I put some parameter ranges, how a logical scenario could look like in the simulator Kala. And the approach in general is to model the causal relation, including its context, as a logical scenario for the assessment in a simulation. And for this, of course, OpenPath can be used. It's very prominently developed in set level and used by VVMethods, or Scala can be used, or other proprietary simulators, of course, as well. And in this case, these are the variables that we need to perform the parameter variation across in order to be able to identify causal effects. And so the last slide will be about the evaluation of such causal effects and modeling quality. On the right, I put a generic causal relation where the variables are just variables. And we can see that we want to evaluate the causal effect of a phenomenon, criticality phenomenon CP, that is realized as a value of a random variable x. For example, CP could be heavy rain and x could be the precipitation. And we want to measure the causal effect on the criticality metric phi. And for this, we use Pearl's causal theory. Of course, this is much too complicated to explain in detail, but we want to evaluate quantities such as the average causal effect. So what is the expected value when the CP is present versus when it's not present, or of course the relative quantity that is the relative causal effect. And on the other hand, we want to be able to quantitatively evaluate whether our modeling efforts are somewhat satisfied or satisfy our requirements. And for this, we could, for example, calculate the extent of explanation of criticality by a phenomenon. So how good did our X really explain criticality as measured by phi? For this, we could introduce a sigma that gives us this extent, and even not more, but equally importantly, we could in general calculate the distances between the probability distributions that are associated with this graph structure in order to check whether we got the dependencies of our random variable x correctly. And for this, we can use various distributions and stochastical distances such as Kullback-Leibler or maximum mean discrepancy. And this is work that's going to be published soon. And you can find more information in the publication. So that's it from the criticality analysis, and I'm going to give the presentation to Philip.
Okay, so thank you, Christian. My name is Philipp Rosenberger, and I will now speak about how the sensor simulation and the simulation as a whole was used and specified and validated in the VVMethods project. So in VVMethods, simulation is now used as test system and as a test instrument, and therefore we have to specify this, and we have to validate if this specification is met. And for sensor models, we came up, actually, this was a four-step method that was developed in the set level project and was then handed over to the VVMethod project. And the first step of this method is to collect the sensor effects for the specific sensor, for example, for a LiDAR sensor. The next step is, if you have this collection of all effects and phenomena that could occur in such a sensor, is to put them in a graph that is a tree-shaped graph. We named it Perception Sensor Collaborative Effect and Cause Tree, so PERCollect. This is actually also an open source initiative. Everybody can contribute as it is collaborative. And in this tree, you start from the top, from the phenomenon. In this case, not a criticality phenomenon, but actually a phenomenon occurring in a sensor. For example, a false negative object. So an object that is actually there is not recognized. And you go down the cause-effect chains to design parameters of the sensor, for example, the wavelengths, and also environmental causes, like, for example, rain and intensity and so on. And with this at hand, you are able to put all these cause-effect chains in an FMEA-shaped table. We call this cause-effect phenomenon relevance analysis, because now you want to know what and which cause-effect chains you want to have in your model, in your simulation, what are more important for your specific system under test. Is it the whole system afterwards, or is it just a driving function, something in between? And also you have to know, at this stage, you have to know the operational design domain, the ODD, and then you put every cause-effect chain from the tree in each line, and then you have to consult two different experts or expert groups. The first one is to score the occurrence of that cause-effect chain, and therefore you have to consult a sensor expert that knows, okay, for this cause-effect chain, for example, you have a false negative object because of atmospheric effects, attenuation, then you can get a specific score from 1 to 9 and also a rational to trace this. And the second expert or expert group is the group that knows the system under test. So you can say how is the impact of this cause-effect chain when it occurs on the system. And if you have scored all of these occurrence and impact numbers, then you can just sum them up and you result in the relevant scores. And now you can decide what cause-effect chains are more important, more relevant to model, that need to be modeled more precisely than the others. The next step, and this is also what we did in the VVMethods project, so we started with a small excerpt, of course, of this percolect tree. We then consulted and the different experts for this excerpt, and then we wrote down the general simulation requirements. We came up with LiDAR sensor system simulation. So a LiDAR sensor system is not only producing a point cloud, but also an object list. So then you have to specify the object list that is simulated and also the detections that are simulated in between to come to these objects. For all these requirements, of course, you have to specify the acceptance tests. And with these acceptance tests, you need to specify the measurement data that is collected and also the reference data and the reference data accuracy. So, for example, how precise do you know where are the objects, what materials, what rain intensity, and so on. And as I said, this is a perfect example for collaboration between the both projects and was performed in collaboration. So how does this look like when you start then afterwards your simulation? Of course, you need a environment simulation, in this case, DSpace tooling, ASM. You have the virtual 3D environment there, you have the sensor environment simulation, and then you come up, or then you compute the generic output, in this case, the reflections, and the reflections are then passed over to the sensor model with the open and standardized interfaces, in this case OSI. And so the sensor model from set level was passed over to VVMethods as a functional mockup unit, FMU, and could be used there. Also, we used a validated material database to ensure the simulation quality. When you then start the validation process, you need to have a test specification for this. And we found a very interesting finding actually that the specification for validating the test infrastructure is actually the same as for validating the automated driving system. So you have meta information, you have the test infrastructure for assessing the simulation test cases, the sequence, and also the evaluation of the success of this validation. And another interesting device I would like to show is that we use a collaborative robot to collect the LiDAR data and also the reference data, because reference data, as I said, is very important. We come to this probably later when there's a presentation about simulation credibility and validation. And in this case, we did measurements of different asphalts to start with, and this work for the validation is still ongoing in VVMethods. So to summarize this, first finding, the assurance framework and argumentation build the basis for an efficient use of simulation. So the requirements and metrics for the credible simulation can be derived by claims and the argumentation strategies. The simulation-based analysis provided by Z-level has then multiple applications within the methodical VVM criticality analysis. So for example, the plausibilization of causal relations or evaluation of safety principles. A second, and I think very great and important finding, is that we had great cooperation between the projects. So for example, with the successful alignment of the test specification and the joint sensor model specification and validation. And I would like to end with the assurance framework, and that it supports simulation and data processes so that exact fit evidences for the assurance argumentation can be provided, which is great. Thank you.